Hi everyone. Can you please confirm if you can hear me? Okay. So I hope I'm audible, right? Great. So let's get started. So today we are going to solve some of the more questions from memory management that we have been solving. So till now we have been solving multi-level paging questions, but today we will go some different questions which are related to access time and all, right? So let me get started. So let's just get started. What we are going to study today. Hi Sumant. Good afternoon. Okay. So let me start. Those who are watching me first time, I'm Sachin. I'm co-founder and instructor at Go Classes, and I have done my masters from ISC Bangalore. After ISC, I have worked at Amazon as an applied scientist. I've also got GATE All India Rank 33. Right. So let's just start with this question. This question has been asked in GATE 90, and what they're asking is that let me just read out this question, that in a two-level virtual memory, right? So we will be solving questions related to TLV, we will be solving questions related to page fault and all, right? Page fault, TLV, and maybe the cache miss, cache miss, or cache hit, something like that, right? So we will be solving questions related to these three topics combinedly or independently, which means in some questions we will be seeing these three topics combinedly, in some questions we will be seeing these three topics independently. So this is the topics, okay, topic of discussion. Now let's just see what they're asking. Okay, before that, before I start any question, can you tell me a flowchart? Flowchart means that if, I mean, what is the first step, and then if you do, let's suppose, I mean, first step should be the TLV, and you hit a TLV or you miss a TLV. Let's suppose you're searching for the TLV, and then you say, right, then you say, this is TLV, and then you say it is, if it is hit, then what's going to happen? If it is miss, then what's going to happen? Something like that, right? So if it is hit, then what you will do? If it is miss, then what you will do? I mean, maybe you will like after hitting, then maybe you will go to the cache. If the cache is available to you, if that is not available, then obviously you will go to the main memory, right? So let's suppose you are going to the cache. And there are multiple complications, whether you are using physically addressed or the logically addressed cache. Okay, physically addressed, virtually indexed, something like that. So we will talk about the type of caches in the COA, but here I'm just keeping it simple. So now you will be asking a question whether this will be a cache miss or the cache hit, which means you are going to find that in the cache or you are not going to find in the cache, right? Something like that. So basically, this will be a huge chart. Look, so what I will do, I will just go through few questions once and then I will draw this chart completely. Okay, so there are few things. I mean, if there is TLV hit, TLV miss, then what we need to do, and then if the cache hit, cache miss, and then if even if it is let's suppose if it is cache miss, then do you have the page fault or not? And then you will be asking a question again whether there is a page fault or not, page fault, right? And based on that, this chart will be little big. So that's why, like, I will do what, I will first go through a few questions so that you are more comfortable with these ideas, and then we will go through this particular chart, right? I hope that is fine to everyone. Let me know if there is any problem in anything. I mean, in technically or non technically, either you're not understanding anything or my voice or video is not perfectly clear. Let me know. I hope everything is okay, right? So let me move further. Now, let's just go to this question. And what this question is asking is that in a two-level virtual memory, the memory access time for the main memory is given to us, which means they have given a time for the main memory access time, which is TM. They are saying if you want to access the main memory, then this is the time that you have, which is 10 to the power minus 8 seconds, right? And the memory access time for the secondary memory, which is TD. So this is the memory access time for the secondary memory. Maybe this will come because of the page fault, right? I mean, you might need to access the secondary memory, maybe just because of the page fault. So this is given to us is 10 to the power minus 3 seconds. What must be the hit ratio H such that the access efficiency is within 80% of its maximum value? Okay. So are you getting this question? Or maybe okay, let's do one thing. Let's just solve a few easy questions. I mean 2 3 easy questions first, and then I will probably go back to that question, right? Reason being is that I just want to start with I just want to get some momentum, and then once you get some momentum with these questions, then we will just jump to that question, right? Okay. Let's just see this question first. If an instruction takes I microsecond and a page fault takes additional j microsecond, so what they are saying is that instruction is taking I microsecond, right? If you want to execute any instruction, then it will take I microseconds, and if there is a page fault, then there will be j microsecond if there is a page fault, right? If there is a page fault, right? So basically they have given that if there is a page fault, then you are going to take some time extra, which is this. Now what they are saying is that the effective instruction time, which means, I mean, if there is no page fault, you are going to execute this. If there is a page fault, then this is the additional time. It's not like that this is the time that you are going to take in the page fault. No, this is the additional time, which means the time without page fault, time without page fault will be something like this, will be I. Now can you tell me time with page fault, how much time you are going to take with page fault? It will be j. Is this correct or there is something wrong? Let me know. Time with page fault. So there is a viewer, Dangerous Kladi. So can you tell me what's your name so that I can identify you later? So time with page fault, can anyone tell me? It will be I plus j, not just j. Reason being is that they are saying that j is the additional time that you are going to take, right? So the total time will be I plus j. Now they are saying the effective instruction time, if on average a page fault occurs at every k instruction, which means they have also given the page fault rate. Page fault rate is on every k instructions, which means there is one page fault on every k instructions. So this is the page fault rate, right? Now can you solve this question? I think now this question is very easy. Just tell me what should be the effective access time for any instruction. So see what you are going to do. You are going to say either there will be a page fault. So you will say if there is a page fault, right? Either there is a page fault, then what is the page fault rate? 1 upon k. Then how much time you are going to take? I plus j. If there is no page fault, then what is the like hit latency, hit rate? It is 1 minus 1 upon k, right? If there is no page fault, then you are going to take just I microseconds. So that's how you can solve it. So 1 upon ki and 1 upon ki will get cancelled out, and then you will be getting j upon k plus I plus j upon k, right? So this should be your answer, I plus j upon k. Can you check which one is the answer? I think A should be the answer, right? Okay. So I hope you understood this question. So A is the correct answer here. Now, like, I mean, you can do this question in this way, where you are saying that if there is a page fault, right? If there is a page fault, then how much total time you are going to take? If there is no page fault, then how much total time you are going to take? Can you tell me? See, this I you are anyway going to take, isn't it? I mean, can you tell me something which you are anyway, which is common? So if something is common, you can always write it upfront. You can say, I mean, there is another way I'm telling you how to do this question. So if something is common, which means you do page fault, there is no page fault anyway, like you are going to take I microseconds, and then if there is a page fault, then how much extra time you are going to take, right? So extra time plus if there is no page fault, okay, no page fault, extra time. So you can, I mean, you need to multiply with the page fault rate also, 1 upon k. Similarly 1 minus 1 upon k into something, right? So that's how you can solve. How you are going to solve? Can you tell me what is the additional time you are going to take if there is a page fault? You are going to take j, right? And what is the additional time you are going to take if there is no page fault? You are not going to pay anything. I mean, you have already paid I, so it is 0. So basically, I mean, you are not going to pay anything additional if there is no page fault, right? So which means I plus j upon k is the answer. So whatever is the common, you can write it first. So this is common in both, right? This is common in both. Whatever is the common, you can write it, and then just see if there is a page fault, what is extra. If there is no page fault, then what is extra. Okay, so that's how also you can take it. Yeah. So Srijit is saying that always take place even in the page fault or the page hit. Yes, that's correct. So that's why you can always take I. So is this method clear to everyone? That how we are calculating it? I mean, just write the common. If there is a page fault, watch it. What is extra? If there is no page fault, what is extra? Right? Just do it in this way. Maybe it will be little bit more clear after some practice. Okay. So let me probably go to the next question. So what they're saying, suppose the time to service a page fault. Okay, servicing a page fault means, I mean, generally it includes the all the time, which means that you are going to go to the secondary disk and then you are going to replace some page or something like that, right? So I mean, generally this is the main memory, and page fault means that your page is not in the main memory, and you are going to bring the page from the disk, from the hard disk. So service time means that sometimes, I mean, they will specify if that is separate, but most probably it means that whatever page you have earlier, you may need to write it, right? You may also need to write it, and then whatever page you require, you may need to bring it, right? So sometimes you do not need to write it, sometimes you need to write it. It depends on the case. I mean, there will be a bit that will say, okay, you should, I mean, there will be a bit that will say it is a dirty page or something, and based on that you need to write it or not, or sometimes you need to write it back, or sometimes you do not need to write it, you just can bring your original page. So basically, generally this page service time includes everything, right? Otherwise they will specify, okay, if it is not including everything. Now what they're saying is that page fault is on an average, okay, like if there's a page fault, they're saying if there's a page fault, then 10 milliseconds you are going to take. Okay, the service time, this is just a service time. Okay, let me just write it in this way. Maybe the page fault service time is 10 millisecond. Page fault service time is equal to 10 milliseconds, right? Okay, while a memory access takes 1 microsecond. Okay, if we are going to access the memory, right, then it is going to take 1 microsecond. Memory access. And memory means main memory, right? 1 microsecond, which is very fast. I mean, compared to this page fault. Then 99.99% hit ratio result in average. So hit ratio is also given. I mean, okay. So basically, this is the page hit ratio, and there will be a page miss ratio, which is the page fault, right? So you can say that that 99.99, which means, let me just write in this way. So if there is a, okay, what you need to do, if there is a page fault, then how much you are going to take. If there is no page fault, then how much you are going to take. Anyway, you are going to spend 1 microsecond, right? You are going to spend 1 microsecond, plus if there is a page fault, then how much extra you are going to take. If there is no page fault, then how much you are extra. So if there is no page fault, I don't think you are going to take something extra. It is similar to the previous one. If there is a page fault, right, page fault rate, then how much extra you are going to pay. You are going to pay 10 millisecond, and if you convert that millisecond into microsecond, maybe you can multiply by 10 to the power 3. This is these many microseconds, right? And then what is the page fault rate? Page fault rate is given to us. It is the hit ratio, so the miss ratio will be 0.01, right? 0.01 percentage, which means 0.01 divided by 100. So you need to write here 0.01 divided by 100. Okay, so here you need to write 0.01 divided by 100. So maybe this if you remove this point, then there will be 2 more zeros. This is 10 to the power 4, this is also 10 to the power 4, so it is 1 plus 1, right? It is 2 microseconds. Yeah, should be 1.999 microseconds. So I'm getting 2 microseconds, but so why I'm getting 2? Maybe because this is 99.99. Okay, so I think if you subtract, yeah, that's correct. Okay, they are saying that if you are going to hit it, then you are going to take only one. Okay, so this time is including, I think, memory access also. Suppose the time to service a page fault is on average is 10 milliseconds. So I think this is covering the memory access also, maybe. Okay, the way the solution is working, it is saying that it is covering the memory access also. Okay, so page fault service time generally means no, it might not be ambiguous question. Maybe I'm not 100% sure that what this page fault service time include. I mean, I'm sure, but maybe like what according to the gate convention that what they have taken. So I think the page fault service time includes everything, which means that including the memory access time also. So let me do in that way, which means. Okay, so if there is a page fault, then how much you are going to take? If there is no page fault, which means there will be no page fault with this much rate, right? Percentage means you need to divide by 100. There is no page fault, then how much you are going to take? You are going to take just 1 microsecond. Plus, if there is a page fault, which means with this much 0.01 upon 100, and then how much you are going to take? You are going to take 10 milliseconds, which is 10 into 10 to the power 3 microseconds, right? Now, if you solve this, you can get the answer. Let me just quickly solve it. So it should be, this is equal to, maybe if you want, you can say that you remove it, then it will be just 1 plus 1 microsecond, and then it will be 0.9999, right? If you divide by 100, it will be into 1, that will be 0.9999, and then this is 1.9999 microseconds. Right? So this is the answer, right? Okay, let me know if that is clear to everyone. Yeah, it is including everything. Yeah, it is not ambiguous. So okay, so Srijit is asking, sir, what are the safe marks in Go classes full length mock test? Actually, I also don't know like how to say the safe marks, but I think our tests are little tricky. And if you are getting I suppose if you are getting some marks which are maybe around 50, then should be good enough. By the way, how much you are getting, Srijit and Devanjan, Akash, how much you guys are getting? Okay. Now let's do this question. In this question, what they're saying, a CPU generates 32-bit virtual address, the page size is 4 KB, and the processor has a TLB which can hold 128 page table entries, right? Okay. And also, maybe we can do one question that I was asking you to solve initially. Maybe let's just do this question quickly, and then we will be moving to some questions related to TLB. So this is the main memory access time that they have given, and the secondary memory access time also given. Now what they are saying, what must be the hit ratio H, right? What must be the page fault, page hit ratio, which is H, right? This is the page hit ratio. such that access efficiency is within 80% of its maximum value. Okay, so what is the maximum value? See, they are saying two level virtual memory has been used. It means that you are going to have two level of page table, right? So just to get that logical address from the logical address to physical address, you require two main memory access, because the page table is in the main memory, right? So two main memory access, and plus one more main memory access to get your data. This is the scenario when there is no page fault, right? Obviously, this is the scenario when there is no page fault. So this is the maximum you can do, right? Is this okay to everyone? That this is the maximum you can do? Which means if they are asking for the 80% of the maximum, then let's just see that what maximum you can do, maybe, right? So this is the maximum you can do, definitely. Now what they're saying, that you are basically performing 80% of that, and to perform 80% of that, what should be your hit ratio? So I hope you are getting what I want to say. Is this okay to everyone, that we are going to take three memory access, right? And maybe let's just see if you are going to have the page fault. So this is when there is no page fault, right? So if there is no page fault, which means the maximum, or maybe let me first write, if there is no page fault, no page fault, then we have maximum efficiency, right? And time in this case, time taken in this case is equal to 3 into Tm. Is this okay to everyone? Let me know. Okay. Okay. Ratul, let's not focus on the question that is not in current scenario. I will come to your point, right? Okay, don't worry. So let's just see this question first. And so in this case, the time taken will be 3 into Tm. Now, what if there is a page fault, right? What if there is a page fault? Now let's just see, what if there is a page fault? Then how much time you take, right? Time taken in this case. I mean, there is a possibility of page fault. Then what will the time you will be taking? What do you think? See, you will be anyway spending some time, like you will be anyway first getting the physical address, right? So you will be anyway spending this much time to get the physical address, to access the page table. I mean, it should be given that page table is always in the main memory. The memory access time for the main. Okay. By default, it should be given that page table are all the page table records are in the main memory, right? So I'm assuming that page tables are in the main memory. It is not in the hard disk. Okay, I mean any of the page table is not in the hard disk. So this is the time that you require to get the physical address, or to access the page tables. Right? To access the page tables, you are going to take it. Now, once you get the physical address, then there will be a chance, right? Then there will be a chance of either there will be a page fault or there will be no page fault. So let me write two terms, plus some time you are going to take if there is a page fault, plus some time you are going to take if there is no page fault, isn't it? Let's suppose the page fault rate is h, then if or maybe let's suppose the page fault hit rate is h. So if this much time you are going to take when no page fault, and 1 minus h into this much time you are going to take when there is a page fault, right? So if there is no page fault, which means you get your physical address, then how much time you need? I think just TM, right? If there is no page fault, then you will be just needing TM. But if there is a page fault, then it will be TM plus TD. Isn't it? Is this okay to everyone? Or maybe you can write something like this. See, you are anyway going to take 2TM to get the physical address. Now, this is the time to get the physical address. Physical address. Now you will go to that address and then you will see either on that physical address the main memory that page exists or not, right? So ultimately if there is a page fault or there is no page fault, you will be just fetching finally, right? Which means if there is a page fault, then you will bring that page from the hard disk, and then once you bring that page from the hard disk, then you will be accessing it, or maybe you will be directly accessing it. So there is some time which is TM, which is common in both, right? I mean, if that is comfortable for you, then you can write directly TM. So TM is time that is in the both. If there is a page fault or there is no page fault, in any way you are going to access this page, right? Now plus what is the time if there is a page fault? Extra time if there is page fault. What is the extra time if there is no page fault? If there is no page fault, I don't think there is some extra time, right? So just TM you are going to take. And if there is a page fault, what is the extra time you are going to take? Page fault rate is 1 minus h in our example, and what is the extra time? I think just TD. So that's also how you can write it. Let me know if that is fine to everyone. Okay. So now what you need to do, they are saying that this much time you are going to take, in general case, and then they are saying this should be the 80% of your maximum, which is 3TM. This maximum time should be 80% of what you are going to take. So this should be, I think, 0.8, something like this. They are saying that whatever time, see what they are saying is that what must be the hit ratio such that access efficiency is within the 80% of its maximum value, which means that this is the maximum value and this efficiency should be the 80% of the maximum value, right? So it should not be lesser than 80%. See, generally, in general, what is the case? Maybe let me write something like this. So this is the maximum you can get. See, this is the maximum, this is the lowest you can get. This is a lower number, right? Lowest we can hope for. And this is the time, see, this is anyway 3TM, and this is the time you are going to get extra, right? So this is the time that extra due to page fault. More time, more due to page fault. So basically, they are saying this is 3TM, and then this is 3TM plus 1 minus h into TD. Now they are saying this should be like this, the lower time should not be lesser than the 80%, which means this should be 0.8 into this. So this time should be within the 80% of this time, right? Okay. So if you solve this, then what will be the h you will be getting? Maybe you can solve it. It is 0.23 TM, right? I mean, if you take this 0.83 TM here, it will be 0.23 TM equal to 0.8 into 1 minus h into TD, and then you need to find this h, right? So maybe you can divide by 0.8. So let me go to the next page. So this will be 1 minus h into TD is equal to 0.2 upon 0.8 into 3 TM, right? And then 1 minus h will be 2 upon 8 to 3 TM upon TD. and then h will be, this is 1 by 4, and which is 3 by 4, 1 minus Tm upon. So this is your final h that you are looking for. You can put the values and then you can get the answer. Is this okay to everyone? If you put the value of Tm and Td, which is given to us, which is I think 10 to the power minus 8 and 10 to the power minus 3, you can get the answer. So 1 minus 3 by 4, 10 to the power minus 3, Tm is 10 to the power minus 8 and 10 to the power minus 3. This is minus 8, this is 10 to the power minus 3, and then it will be I think 10 to the power minus 5. So what is the answer that they are getting? Okay, let me see the answer. It is coming out to be 99.99%, somewhere around it, right? 99.99%. So it is 99. Okay, should be that much only. So h is 0.75 into 10 to the power minus 5, right? 0.75 means 3 by 4 into 10 to the power minus 5. So this is 3 by 4 into 10 to the power minus 5. So 1 minus this is coming out to be 99.99%. So I hope that is fine to everyone, right? Which equation you are talking about? This one. See, this is what you are anyway going to take to get the physical address. Now, once you get the physical address, there might be a page fault or there might not be a page fault. But anyway, in both the cases, you are going to, what is common? You are going to anyway access this page, which is this. If there is a page fault, then you are going to get you are going to take this extra. If there is no page fault, then you are going to take nothing extra. So that's why I am not writing it, right? If there is no page fault, then you are not going to take anything extra. So this is no page fault. This is common, right? This is common, sorry, this is common. Once you get the physical address, this is common. This is the case where there is a page fault, right? Otherwise, what you can do, you can write in that way also, which means you can say that 2Tm to get the physical address, plus if there is a page fault or maybe H is for no page fault, then just Tm. If there is a page fault, then Tm plus Td. This is also fine, right? These two formulas are actually same, because this will also be like, if you just sum this and this one, this will also be Tm and then plus 1 minus H into Td, because 1 minus H into Tm and H into Tm both combinedly will be just Tm, right? And 1 minus H into Td is same. So basically, I mean, either you write like this or maybe you can directly write like this. Both are fine. Let me know if that is okay to everyone, right? Okay. So this is if there is no page fault. I mean, H here is for no page fault and 1 minus H is for page fault. Okay. Let me move further. Okay. Now let's solve some questions related to TLB. Now what they are saying, a CPU generate 32-bit virtual address. The page size is 4 KB, right? So virtual address space is given to us 32 bits. Page size is also given to us. 4 KB means this is I think 2 power 12, right? 2 power 12 bytes. The processor has a TLB which can hold a total of 128 page table entry. So TLB size is also given 128 entries. It can hold 128 entries. Do you remember what is TLB? TLB used as a cache for the page tables, right? We do have the page table entries in the TLB. Okay. Now what they are saying, a processor has this, okay, page table entry, and this is 4-way SAT associative, right? So they have given the TLB is 4-way SAT associative. It means one set size is 4. So can you tell me number of sets here? number of sets will be, if these many lines are or these many entries are available, and one set is having the four entries, I mean there is a set of 4 entries, so I think this will be 32, right? 32 sets, which is 2 power 5 sets are available with you. Now if virtual address space is 32 bit, out of these 32, you will say that 12 is going for your block number, right? Or the page number or something, and then this is remaining, which is 20. Out of this 20 is I mean this is for block offset, this 20 is for block number, and then you will say out of this 20, this 5 will go for your set number, because these many sets are available, and then remaining is the TLB tag. This is tag. So how much is remaining for the tag? It is 20 minus 5, which is 15, right? Yes, okay, that is correct. So 20 minus 5, 15, which means you can say that 15 is the correct answer. So C is the correct answer, right? Okay. So I hope that is fine to everyone. Let's just check the answer. So the page table size is of 4 KB. The offset is this. Yeah. So these are the number of sets, and that's why the C is the correct answer. Now there are some concepts that are particularly not like directly applicable here, but there are some concepts related to virtually indexed, physically tagged, and these kind of things. I mean, they have not asked these concepts very regularly, but we will see this in the computer organization. Okay, when I or Deepak takes the computer organization cache classes, then maybe if there is some doubt here that what is set associative and these things, then it will get clear. Now let's go to this question. What this question is saying, the page fault service time be 10 milliseconds. Okay, so they are saying the service time is given to us, service time, which includes everything, right? Is 10 milliseconds in a computer with average memory access time. Okay, memory access time is given, which is very less compared to the page fault service time. So it is memory access time. It's given to us. It is 20 nanoseconds. If one page fault is generated every 10 to the power 6 memory accesses, right? So page fault rate is given to us. Page fault rate is 1 upon 10 to the power 6. What is the effective access time for memory? Yeah, so they are asking effective memory access time. Memory access time. So it is, I think, very easy question. Either there will be a page fault or there will be no page fault, right? So if there is a page fault, then then this will happen with this rate, and then you are going to take, I think, only 10 millisecond, right? And 10 millisecond, if you convert that to nanosecond, then probably you can say that I think this is difference of 10 to the power 3, this is 10 to the power 9, so difference of 10 to the power 6. So maybe you can say 10 into 10 to the power 6, right? Okay. These are the nanoseconds. And then if there is a page fault, then this much you are going to take. If there is no page fault, which means with this rate, you are going to take 20 only, right? So if you solve this, see, if you solve this, then it will be 29.99998 nanoseconds, which is almost same as 30 nanoseconds. So case is asking, are cache and TLB are two different concepts or they are linked? See, these are, having the same behavior. It is just that TLB is also a cache. Generally, TLB size is smaller than the actual cache, because we just need the fewer entries there compared to the cache in which we actually store the data. Okay, so the TLB is also cache. If you are little bit confused, then just consider TLB is also cache. It is a separate cache where we just store the page table entries. Okay, now let's do this question. What they are asking: consider a paging hardware with a TLB, assuming that entire page table and all the pages are in the physical memory, right? So consider paging hardware with a TLB. So they are using the TLB, that's what they are saying, and assume that entire page table and all the pages are in the physical memory, which means like what does it mean? Like it means that for the page tables, if there is a TLB miss, then you will need to go to the main memory, right? So either, see, either there will be a TLB hit or TLB miss. In case of TLB miss, they are saying that you need to go to main memory to get page table. And during this process, whenever you want to go to the main memory for the page table, I'm not saying for the page, right? For the actual page, I'm not saying, but for the page table, if you want to go to the main memory, then there is no page fault. That's what they are saying. I mean, entire page table and all the pages are in the physical memory. Okay? So all the pages are in the physical memory. You do not need to worry about that. Okay, what if the TLB misses there? Then will I be having the page fault or not? For the logical address to physical address conversion, right? So this is what we have assumed in the earlier question also. I think, yeah. I think in this question also, what was that question? The 2 and 3 was given, right? 2 TL and this was given. So yeah. So I think for this question also we have assumed that all the page tables are in the main memory, which means for the page table, just to access the page table, I do not have to have the page fault, right? So that's what we have assumed. See that if like this is what you are anyway going to take to access the page table. So we are not saying that you need to go to the hard disk for the page table, right? This is what we are saying for the page table, and here I do not need to deal with the hard disk. Okay, so I hope that is okay. Now let's just do this question. Okay, it takes 10 milliseconds to search TLB and 80 milliseconds to search in. So TLB access is given to us. TLB time is 10 milliseconds. Search the TLB and 80 milliseconds to access the physical memory. Okay, so main memory time, if you want to access the main memory, then main memory time is given to us. It is 80 milliseconds. TLB hit ratio is also given. TLB hit is also given to us, which is 0.6. The effective memory access time, they are asking about effective memory access time. Okay, so they are using the paging and paging hardware with the TLB. So what is your first step? You will go to the TLB. Either it will be hit or it will be miss, right? So maybe let me go to the next page, and let's just see using the two methods. Two methods means directly or maybe with little longer approach. So either there will be TLB hit. If it is hit with this much, and how much time you are going to take with TLB hit. If this is miss, then this, right? So if there is a TLB hit, then how much time you are going to take? Then maybe you are just going to take 10 milliseconds, because that's all, right, for the TLB hit. If there is a TLB miss, then anyway you have just accessed the TLB plus you are going to access the main memory, isn't it? So this will be your effective memory access time. Let me know if that is understood, right? See, sorry, this is 10 plus, okay, we need to get the data also. So this is 10 plus, obviously you need to get the data, which means that there will be one memory access you will be requiring to get the data. So 10 plus 10, sorry, 10 plus 80. This is 10 plus 80, 80 milliseconds, and this is 10. If this is TLB miss, you just I mean you just have to you just access the TLB, and then to get the physical address only you access this 80 milliseconds, and then to get the that page, right? I mean from this physical address to access the page, you need to have one more 80 milliseconds. Right? So this is your total effective memory access time. Right? That's what they are asking. that what is the effective memory access time. If you want to actually access any memory, then how much time you are going to spend. First you will go to TLB. If it is hit, then you are going to take you are just going to take the TLB time, and then whatever is the time that you need to spend to get the page. If it is miss, then TLB time plus one more time to get physical address, plus this is the time for the main memory access. Now can you also do it using some shortcut? Okay, so tell me, if this is TLB hit or TLB miss, then what is common? What is common in both? I mean, I think you will anyway go to TLB, right? You will anyway go to TLB. You will anyway also go to the to get the page. You will anyway go to TLB, right? TLB access and final page access. Page access means like once you get the physical address, and then I mean you will be finally accessing this. So that's what you anyway have to do. Okay, now tell me, what is the TLB hit? This is 0.6. If this is TLB hit, what extra you are doing? Plus if it is TLB miss, what extra you are doing? So if it is TLB hit, I think you will go to TLB, and then you will follow the same path, right? Then you get the physical address, you will go here. I think there is nothing extra you are doing, because this is the same path you are doing. And if it is TLB miss, then you have the TLB first thing, right? This is done. You went to the main memory to get the physical address. This is not I have written here, and then you finally access the page. So basically it will be something like this, right? So effective memory access time, you can also write some in this way, which is 90 plus 0.4 into 80, right? Which is 320 and then 32. So it is 90 plus 32. It is coming out to be 122 milliseconds. So answer should be 122 milliseconds. Let me know if that is clear to everyone. Right? So you need to write what is common, I mean what you anyway do, and then whenever you are doing the TLB hit, then just trace out from the beginning. Okay, what you are doing? You are going to TLB. Okay, I have written here. You are going to get the page. Okay, I have written here. So nothing extra you are doing, right? So zero extra. Whenever there is a miss, what you are doing? Just trace out from the beginning. You are going to TLB. Okay, I have written in the common. If this is a miss, since it will be a miss, you will go and find the physical address. So that's why it is 80, and then you will again be finding the final page. So that's what I've written in the common. So you do not need to write it here. So that's why this is common. What is extra in TLB hit? What is extra in TLB miss? Something like that, right? Okay. Let me know if that is fine to everyone. Okay. So let's just move to the next question. Right? So what they are saying, I think this question is easy. Let's just do it. What they are saying, a computer system implement 40-bit virtual address, page size of 8 kilobytes. So this is 40-bit virtual address, right? Okay. Page size is 8 kilobyte means if you can convert it, it will be 2 power 13. Right? So which means 13, and remaining is your block number, which will be I think 27 bits, and 128 entry TLB, okay, organized into 32 sets having 4 ways, okay, which means the set number is given to us is 5, so it will be further divided into 5, and then this will be 22 will be your tag. So this is tag, okay, minimum tag bits they are asking. This is set number. Yeah, this is a very easy question. You can easily do this question. The answer is 22, right? Let me know if that is okay or there is some issue in this question. Okay. Now let's move to this one. What they're saying, consider a process executing on operating system that uses the demand paging. Demand paging means just like a virtual memory, right? I mean, virtual memory can be implemented with any of the method. The core idea of the virtual memory is that you can put some of the pages or maybe some part of your process in the hard disk. That's what virtual memory says, and that this demand paging is just one of the very popular way to implement the virtual memory. The average time They're saying we are using the virtual memory. You can just consider this demand paging as just like a virtual memory. Okay, just like a virtual memory. I mean, there may be a page fault and all. I mean, you are allowed to store the pages in the hard disk. The average time for the memory access in the system is m units. So m is for the memory access. Memory access time is m, and then what they are saying, and the d units if the memory access causes the page fault. Okay, so page fault service time, right? Page fault service they have given to be d. Now it has been experimentally measured that the average time taken for a memory access is in the process is x units. Okay, so they are saying that average effective memory access time is x units. Which of the following correct expression page fault rate? They are asking about the page fault rate. I think that's very easy question. I mean, should be easy question. I'm not sure. Let's just try to solve this question, right? So this data is given. They are asking for the page fault rate. Now, effective memory access time should be, if there is a page fault or there is no page fault. Let's suppose if there is no page fault, then you are just going to take m time, plus if there is a page fault, then you are going to take d time, right? And then x is equal to 1 minus h into m, which is basically m minus mh plus hd. So it should be x minus m upon d minus m, right? So h should be x minus m upon d minus m. I think B should be the correct answer, x minus m upon d minus m. Yeah, so case is asking, is there any difference between minimum tag bits and maximum tag bits? I think you are asking with reference to this question, right? So like tag bits, I mean generally we do not store anything other than this the general tag bits, but yes, I mean you can always store some other things in the tag bits. So minimum means like whatever is your virtual address division, and from there whatever is the tag number of bits you are getting, it is the minimum. If you want to store some other things in the tag, it is up to you. So I mean you can store some other bits also, right? Okay. And if you have gone through the text or maybe the video, then you might know that we are using the comparators here, right? So we will be using the comparator here, and comparator is only on these number of bits. Although you can store some other bits, but the comparator will be generally on these number of bits only, right? Okay. Now let's try to solve this question. What they're asking is that, okay, please let me know if everything is fine to everyone or there is some issue. So that's very easy questions. Like all of the questions were easy. So I think it should be doable. You like doable questions only. Let me just do maybe 2-3 questions, and then we will move to some good questions also, right? Okay. Let's just solve this question then. What they are saying, that assume that in a certain computer the virtual addresses are 64-bit long and the physical addresses are 48-bit long. So virtual address space is given to us which is 64 bits. And physical address space is given to us which is 48 bits. Now what they are saying is that the memory is word addressable. Yeah, that's very nice. Memory is word addressable at this point in time, which means that this physical address space which is 48 bits. So total you can have 2 power 48 addresses that you can map. I mean 2 power 48 words basically, right? So each of the physical address or each of the virtual address will be representing one word address. Okay, so basically these many, not bytes, you will say these many words. This is the address for these many words. I mean you need to have everything in the words only. Okay, I mean you need to actually convert it. Initially it will be in the bytes only. So this is the bytes, and then you need to convert it based on the given data, right? Now what they are saying is that the page size is 8 KB. So page size is 2 power 13 bytes. You can convert that into word also. This is 2 power 64 bytes. You can convert that into word also. And word size and byte, I mean the relation between word size and byte is given, which is 4 bytes, right? So can you convert each of them into into the words? Do you want to try this question for a minute? Let's just try to do this question, because this is a little different question that what we have already done. Just try doing this question. Okay, so probably you have tried it, right? So let's just see what is the answer you are getting. Okay, Akash is getting B. Let's just see that what is the correct answer. So what they are saying is that the memories were disabled this time. So Akash is getting B. Let's just see what does this mean. So page size is given in the bytes. Can you convert that to words? I think this is 2 power 13 bytes, which is 2 power 13 upon 4, which is 2 power 2. Right? These many words, which is 2 power 11. Is this okay to everyone? The page size is actually 2 power 11 words. Now, what they are saying is that virtual address space and the physical address space is 64 and 48 bits, contiguously. So basically, okay, let me just tell you what does this mean actually. So basically, it means that you can actually access 2 power 64 different addresses using the virtual address space, right? Now tell me how many words you can access. So which means that what I'm asking is that, so suppose that your, let me just write, the physical address space is 48 bits and your word size is 4 bytes, right? 4 bytes. Now what I'm asking, what does this word means? Word size means smallest addressable unit, right? Smallest addressable unit. See, you have 48 bits available for you, which means you have 2 power 48 different addresses available for you, right? Different addresses available with you, right? I mean, you can represent 2 power 48 different combinations with 48 bits. Is this okay to everyone? You can definitely represent 2 power 48 different combinations with this 48 bits, right? Now, what I want to ask is that if you can represent these many, I mean, you have these many combinations with you, and you want to address every 4 bytes, right? You have to address every 4 byte, not every byte. If you just have to address just a 1 byte, then maybe you can address at most 2 power 48 bytes. But here, since you have to address all, like in all of these 4 bytes can just accommodate, you can just accommodate one address, right? And you have 2 power 48 addresses. So how many bytes you can address? Like total, what is the size of the physical address space in the number of bytes? Size of physical address space in bytes. So basically, this always means like if you have given that 2 power 48, then it is always means words. Okay, sorry, I think I have written the bytes earlier. So it should be the words, because these many different addresses are available for you, and for each address you will just represent one word. Each address will just represent one word. So how many? What is the size of physical address space in terms of bytes? Okay, if this is 2 power 48 words, and one word is of 4 bytes, so that is why it is 2 power 48 into 2 power 2 bytes, right? Is this logically understood to everyone? The physical address space is of 48 bits. Then what does this mean? You have 2 power 48 different addresses available with you, and you will be addressing, with each address you will be addressing one word, right? Which means you have 2 power 48 different words available with you, which means you have 2 power 48 into 2 power 2 bytes available with you, right? Okay. Anyway, this is not the question is asking. The question is saying the page size you have calculated is 2 power 11 words, right? So the page size was given to us in the bytes, but now we have calculated in the words, which is actually 2 power 11 words. Now what they are saying is that the TLB in the address translation path has 128 valid entries. Then how many distinct virtual addresses can be translated without any TLB miss? Okay, so they are saying how many distinct virtual addresses you can have without any TLB miss, which means in a TLB, how much maximum you can store at a time, how many maximum addresses you can store at a time. See, what is happening here? For each word there will be one address, right? Each word will be having one address. So each word has one address. So suppose in this TLB, how many entries are there? 128 entries are there. Now each entry is basically accommodating one page, right? One page, which means if I access any of this 2 power 11 words, then this entry is enough, right? Which means there will be 2 power 11 words. If I either access any of them, then this is just this can be served by this entry only. One entry is actually serving one page, which is actually 2 power 11 words. So if there are 128 entries, then for 128 into 2 power 11 words, there won't be any miss, right? No miss. Because if I'm accessing any address, let's suppose 0100010001, let's suppose this is belonging to the page 1, right? Page 1. Then I will go to this entry. Or let's suppose if I go to some other address which is 0001, let's suppose it is also belonging to page 1. Okay, suppose it is also belonging to page 1. Then also I will go to this entry. Similarly, there are 2 power 11 addresses that can be served by just one entry, right? Because it is telling me that what is your page number corresponding to this address. Okay, so corresponding to this address, what should be the page number? That is what it is telling me. Is this okay to everyone? So what we are doing, see, there is a TLB. What I am asking is that this TLB holds how many entries? Okay, let me just first ask, this TLB holds how many entries? It is given that this TLB holds 128 entries. Okay, it is given to us, which means 128 pages will not be having any miss, right? 128 pages. Is this okay to everyone? And 128 pages means that how many words basically? One page means 2 power 11 words. So total 2 power 11 into 128, or maybe 128 into 2 power 11. 128 into 2 power 11. These many words will not be having any miss. So total these many words can be served without any miss. These many distinct words can be served, which means if CPU generate maybe one of this address, this is basically every word is having one address. So CPU generate these many addresses. For these many different distinct addresses, I will not be having any miss, right? Okay, so I hope that is fine. So I think the answer is 128 into 2 power 11, which is same as 256 into 2 power 10. Right? I mean, you just take 2 from here to here. So now let's move to the next question. Yeah. So what they're saying, a paging scheme uses a TLB. A TLB takes 10 nanoseconds and the main memory access takes 50 nanoseconds. What is the effective access time if the TLB hit ratio is 90% and there is no page fault? They have not given the page fault. So I think you can do it. This is very easy question. If there is a TLB hit, then how much time you are going to take? You are going to take time for TLB, which is I think 10, and then obviously the main memory. If there is a TLB miss, which is with this rate, then you will go to TLB, you will go to main memory twice. That's all, right? Or maybe you can write in this way, because this is common, and then whatever is the extra, you can write 0.1. So this is 60 plus 5, I think 65. So C is the correct answer. Okay. So I hope you understood this question. Yeah, C is the correct answer. Now let's just do this question. This question I have taken from one university, and this question is little big in the sense that they have asked everything related to TLB, cache, page table and whatnot, right? I mean, you have the TLB, you might be having cache also, you might be using the paging also, and that's why there is a page table, and there might be the page fault also. So whatever you have, let's just combine all of them and let's just do this question. So they are saying that TLB hit requires 5 nanosecond. Cache hit requires, if there is a cache hit, then cache will require 12 nanoseconds. A memory reference will require this much. A disk reference will require 200 milliseconds. This includes updating the page table, cache and the TLB. Okay. So anyway, the disk reference, just a disk reference requires this much. So the memory reference is separate and the disk reference is separate. Okay. Do you remember one question where we did TM, TD? So this is just like a TD, okay, where the TM is this, this is TD, this is TD. That's what it is given to us. Now, the TLB hit ratio is 90%, okay, the cache hit ratio, the page fault rate, everything is given. On a TLB or the cache miss, okay, if there is a TLB or a cache miss, the time required for the access includes the TLB or the cache update. So they are saying the TLB, if there is a TLB or cache miss, the time required for the access, okay, includes a TLB and or the cache update, but the access is not restarted. So basically, like this time, okay, this 5 nanoseconds, you can just assume that this time is including everything. If there is a miss, then also you can just take this time. You do not need to take extra time just to update the TLB and all, right? So let's not worry about it. On a page fault, the page is fetched from the disk, all updates are performed, but the access is restarted. Okay. All references are sequential, which means there is no parallelism that we are doing. So let's just see that how to solve this question. Okay. So let's just see step by step. So first you will be checking the TLB, right? Either it will be a hit or it will be a miss. Let me write in this way. So maybe it is a hit, maybe it is a miss. Let me know if things are fine till this point. So what we are going to do, we are just going to analyze this question little carefully, which means we will just see that what's going to happen in case of TLB hit or TLB miss. So suppose there is a TLB hit, which means you get the physical address, right? Which means you get the physical address. We have physical address. Now we can directly go to cache. Okay, so there is something called virtual index, physically tagged, and these kind of things. Let's not worry about it. Actually, you will be needing the physical address anyway, right? Until and unless it is virtually indexed, virtually tagged, which means like everything is you are doing with the virtual address to the cache. Then this TLB hit and TLB miss won't matter for that cache. Okay, if that cache is just a one type which is virtually indexed, virtually tagged. Okay, I will talk about it in the Koa, but if that is the tag virtually indexed, virtually tagged. Okay, I will talk about these things in the Koa, which means everything is virtual. Then you might not be needing the physical address for the cache. But we will talk about whether this kind of cache exists or not, or we will talk about this later. So we have the physical address at this point, and then we are going to the cache. Right? So we are checking the cache here. Now you will say there will be either hit or there will be miss. Right? Let me know if that is fine to everyone. So you will be checking the cache, there will be hit or miss. Now in cache also you will say like, I mean, if there's a miss. Okay, just a second. So they have the page fault also, right? Okay, now tell me, in case of cache hit or in case of cache miss, what will be the difference and what is the common? Just think about it. So what I want to write here, I want to write what's going to happen in case of cache hit or in case of cache miss. So if it is a cache hit, then what we are going to do? I think we will just return from there. I don't think we need anything else, right? I finally got what I want to access, so I will just return from there, right? If there is a cache hit, then it's a best case. TLB hit, cache hit. I mean, I don't need anything else, right? If there is a cache miss, so if there is a cache hit, so I will say that I'm done. TLB hit, cache hit, both are in my favor, so I will say I'm done, right? If there is a cache hit. Okay, let me see the questions. Page fault means we have to go to the secondary memory. Yeah, page fault means if there page fault means page fault means we have to go to the secondary memory. If there is no page fault, does this imply we don't have to go to the disk? Yes, if there is no page fault, why will we going to the disk, right? Okay. Now tell me, if there is a cache miss, then what you are going to do? Then obviously you will go to the main memory, right? If there is a cache miss, then you will go to the main memory. So let me write in this way. Now, if the cache miss, then you will go to the main memory. Now, going to the main memory also have two cases. Hit means no page fault, and miss means there is a page fault. Now, This is little on the controversial or the debatable part, that if you have the TLB hit, then can we have the page fault, which means the cache, let's not worry about the cache and all. If there is a TLB hit, I get the physical address, and let's suppose I'm going to directly by the main memory or maybe via cache means let's not worry about it. So here, like the page fault means that there will not be a page in the main memory. Okay, so there are like there are some subjective definitions of the page fault also, which means that page fault, people say that in this case also page fault may exist, but the page fault definition is different, where they are saying that in this case also if there is a page fault, okay, then this page fault means that, see what this TLB hit means. So my question is that you get the physical address using the TLB. Now can there be a page fault, which means the TLB is saying, TLB hit, TLB is saying you get the physical address, and using this physical address you go to cache first, and then bypassing the cache, after the cache means you are going to the main memory or not, let's not worry about it, but let's suppose I'm directly going to the main memory. Now since there is a TLB hit, which means TLB is saying that okay, you go to that physical address, then do you think that there can be a page fault? Can there be a page fault? See, page fault means that page does not exist in the main memory. You have to bring it from the hard disk. Now, if there is a TLB hit, then obviously, okay, obviously it means that that page should be there, because if the page is not there, then the moment I'm bringing from this or I'm throwing this page from the main memory to the hard disk, okay, the moment I do it, okay, the moment I throw this page from the main memory to the hard disk, and that's where the page fault had come, right? So see, let's suppose I'm talking about today. So today I got a page fault. Why? Because yesterday maybe I have brought this main memory that page from the main memory to the hard disk. Then only I must have got the page fault. But yesterday only, when I'm getting this page fault, I'm throwing this main memory to the hard disk. At that time only I should have set this TLB. I should have updated this TLB. I should have said that okay, now this time this is not hit. You're getting my point? What I'm trying to say? Okay. So what I'm saying is that, see, if there's a TLB hit, then it means that the page must be there. The page must be there in the main memory, because if page is not there, then TLB must have updated the yesterday only. I must have updated TLB yesterday only, right? So we will say that in case of TLB hit, there will not be a page fault. Okay, there can be a page fault, but the type of page fault is different. Basically, if the TLB is there, then in the main memory your page is there, that's for sure. Okay, in the main memory, although that is debatable and I have not read all the text about it, but according to the standard reference, I am telling you that in case of, if this is TLB, and in case of the page this TLB hit, okay, in case of TLB hit, I am saying that page must be there. This must be there in the main memory. Now, what may happen that whenever you are going to this page, then it might be having some security access, maybe the write protected. Okay, maybe this page is write protected, which means you cannot write it. In that case, you will be raising some interrupt, which means let's suppose you in your program you are writing something. Okay, in your program you are writing some const int I equal to 5. Okay, and then you store this into some location, and which is here I equal to 5. This is in some page. Okay, and then this is your main memory, and now you suddenly access this location, and you want to write I equal to maybe 50. Okay, now at this instruction CPU will generate this address I, right? CPU will say that okay, I'm assuming there is no compiler error and all. Okay, so it might happen at the runtime that you are accessing some memory which you are not supposed to access. So CPU will generate this address I. CPU will say that okay, get me the address I and update to 50. TLB will say that yes, that particular page is present in the main memory. But when you go to the main memory, you will say that okay, the page is present, but I cannot modify this page. So in this case, there will be interrupt, right? And this is also, I mean, in some of the text, this is also considered as a page fault interrupt. I mean, this is also served just like a page fault interrupt. So anyway, let's not go to much of the theory. So what I'm saying, if there is a TLB is saying yes, then the page must be there in the main memory. Okay, this is what we are assuming currently. So I'm saying, yeah, this is debatable, and I have not read all the text, to be very honest. Okay, so I will clarify if there is something else I found it later, but currently we are assuming if there is a TLB hit, then in this case go to main memory, go to main memory and done. I mean, you just go to main memory, fetch the page, and you're done. Either you go to cache, if there is nothing in the cache, then you will go to the main memory, and then you're done, right? Let me know if this part of diagram is clear to everyone. So Devananjan is asking, sir, one doubt, TLB is cache. No, TLB is a cache, but it is just like a cache. It's not like the cache for the data. It's like a cache for the page table, right? So TLB is also cache, but it is not the cache that you are saying. It is the cache that is for the page table. So this TLB and the cache is actually different. This is containing the data. This is containing just like page table entries. Okay. Now, what if there is a TLB miss? In case if there is a TLB miss, then what you will do? You need to get the physical address. You will go to the main memory, right? If there is a TLB miss, then what you will do? You will go to the main memory. So yeah, this is very interesting. Now, uh, so what you need to do? You need to go to the main memory, and then you need to first convert that to a physical address, and then you will be checking that what's happening, right? So maybe go to the main memory. Go to main memory and get physical address. Now here I am currently assuming that if you are going to the main memory, your page tables are at least in the main memory, right? I mean, what I am saying here is that your page tables are always in the main memory. You will not be having any difficulty. Okay, is this fine to everyone? Let me know if that is fine. See, what I am saying, that if you go to if you go to the main memory, you will always be finding the physical. You will always be finding the page table. So basically, the physical address will not raise any page fault. Okay, this is what we are assuming here. Or maybe we can modify the question, right? We could also say that physical address, to get the physical address also, we are raising some page fault. So but generally, if this is just one label page table, then we keep that page table in the main memory always. Okay, so anyway, let's keep it simple. So we get the physical address, then again we will be going to the cache. Now go to the cache. Right, we will go to the cache, and then we will be asking whether we get the physical address. It is hit, then we are done. Now again, if it is miss, then we go to the main memory, and we will be asking whether it is a page fault or not, because in this case page fault can occur, right? There is a, so we go to the main memory, we will be asking whether page fault or no page fault. If there is no page fault, we are done, right? If there is a page fault, then go to secondary memory, and store the page in memory. That's how this flow will work. Let me know if that is fine to everyone. Okay. So let's just do one thing. What we can do, either you can solve this question by yourself. Okay. So I will solve it tomorrow. Don't worry about it. I will solve it tomorrow. So there is an answer of this question. Either you can try solving it and then just try solving the GATE 2020 question. Okay, this question. So that's what we can do, or maybe I can solve it now. So what do you think? Should I will be solving it this tomorrow or now? Because I want you to just practice this question, because this is some big question where all the possibilities are covered, right? So should I be covering now or tomorrow? Actually, I want to keep my video length not more than 1.5 hours. So this is the flow chart. Maybe this flow chart will help you. And then what you can do, you can just try this question and then we can meet tomorrow to solve this question. I will immediately update the slides here, right? So that you can get the answer also. Okay, this is the answer of this question. Okay, okay, you can try, right? So we will be meeting tomorrow, maybe at 2 p.m. or if there is some changes, I will just let you know. And then tomorrow, after these two questions, we will be starting deadlock, right? And once we finish the deadlock, I think deadlock will just take 1 day, and file system management will also take just one more lecture. So I think just two more lectures are there in the operating system, and after those two lectures, we will be starting computer networks, right? So I think we have covered most of the questions in the operating system from almost every of the topic. If still there is some doubt in any PYQ, you can just send me. We will be covering in the last